Welcome everybody to today's presentation. My name is Mark Atkinson of Wiley Wilson, and today we're going to be talking about campus electric utilities, utility-owned or campus-owned. The course objectives for today: we're going to explain how electric energy is delivered to your campus. We're going to explore options for on-site electrical distribution. We're going to explain how electric rate schedules work. We're going to demonstrate rate schedule sensitivities to energy procurement strategies. We'll explore how on-site generation may affect the economics of energy procurement, and we'll discuss factors that influence the feasibility of different electric or energy procurement strategies. Let's talk a little bit about how we get electric energy to your buildings on your campus. So we're focusing primarily today on college campuses, but the concepts that we talk about today are also applicable to medical campuses, military bases, and any kind of multi-building campus, industrial headquarters, industrial complex, that sort of thing. And when we're speaking of energy today, we will be concentrating primarily on electricity, but if we incorporate on-site generation, we also have some options for bringing heating, cooling, or domestic hot water production to your campus as part of the energy package. Let's talk for a minute now about the power delivery system. The power delivery system originates at the generating stations. We have a wide variety of ways that power is generated these days. You can be looking at a traditional power plant with natural gas, coal, or nuclear. You can be looking at a hydroelectric station, or you can be looking at renewable energy plants. And these may be distributed over the service area and make multiple connections to the transmission system. Once the electricity is generated, then it's transmitted over a transmission system. These are typically what you see running across the countryside, the steel tower lines or large steel poles. Voltages on these systems range from 44,000 volts up to 750,000 volts, and their purpose is primarily to move the power in bulk from the generating locations to the centers of load like cities, towns, or large users. Once the transmission line gets into the vicinity of the users, then we step the voltage down to what we call distribution level voltage, sometimes referred to as primary voltage, in the range of 34,500 volts down to as low as 4,160 volts. This power is typically transmitted throughout the vicinity of the load, typically on aerial pole lines, but it may also be distributed underground in more urban areas. This would be the wood pole lines that you see running down the sides of the streets, or if you go into a developed area, the green boxes that you see along the sides of the road. Once you get to the site, and in this case, let's talk about your campus, then we're talking about typically underground distribution at the primary voltage, and then at each center of load, at each building, at each user, you'll be looking at having typically a pad-mounted transformer. There may be one or more buildings per transformer, and then the voltage will be stepped down to the building utilization voltage, which is somewhere between 208 volts and 480 volts on most buildings. In a utility-owned system, each building will typically have a watt-hour meter on it to collect the watt-hour usage data that they use in preparing your bill. On the screen now I have a couple of photographs. This will be in your handouts that show photographs of each of these items that you can look through and just see what they look like in real life. So what are the options for the on-site utility distribution? And when we're speaking of on-site utility distribution, we're talking about the primary voltage distribution that goes between the buildings, then the step-down transformers at each building, and then the service facilities that feed the building individually. So if we go with a traditional utility-owned system, what we're talking about here is the utility owns the primary voltage or distribution voltage lines on the site going between the buildings. They'll have an individual meter on each building. They may share a transformer between a couple buildings, or each may have its own. The options that we have here for the owner would be a possible redundant upstream primary source if it's available, usually at a premium cost. In this system, each building is going to have a separate account, so there'll be a separate bill for each building. The option to this is that the campus owns its own electrical distribution system. So we'd be looking at a single meter at the primary or distribution voltage and a single account. So this consolidates the entire area into one bill. If you have a large system, you may be looking at owning a main substation. You'll be looking at underground cabling, usually in some kind of duct system. You may have some switchgear scattered around the campus to distribute to different buildings, and then you'll have the distribution transformers and services. There is some possible upstream redundancy here as well. You may be able to get more than one delivery from the electric utility, typically also at additional cost. Other options that we have: if you own your own system, it makes it very easy to integrate campus-owned on-site generation systems. Larger scale generation integrates well into these types of systems, and you can actually go into what's referred to as a net metering arrangement. When we talk about net metering, what we're speaking of is you put a certain amount of generation on your system to offset a certain amount of power purchase from your local utility. So just by way of example, using some round numbers, you might have a system that pulls 1,000 kilowatts of electricity. You may install 250 kilowatts of generation, meaning that your net purchase from the utility is now 750 kilowatts. This is typically used to take advantages of features of rate schedules where if you can control your peaks, you can save money. Now, if you do have an electric generation system on your campus, you can be looking at energy, not just electricity. The waste heat that comes from a generating system can often be used if you've got a good use for it on campus, especially if you run a central heating and cooling plant, for heating purposes, for domestic hot water, for chilled water, or for supplemental electricity generation. You can be your own utility. There are some campuses, especially larger campuses, that are completely off-grid. They have a combined heat and power generation system that supplies all of their electricity needs, a significant portion of their heating loads. It may supply a significant portion of their cooling, and basically it allows the campus to go completely off-grid, leaving the utility as a backup for emergencies. So why would you decide to do a system? What tips the scale? So we have really a couple of things to look at. We have simple payback to look at, and then we also have some variables and intangibles. Your simple payback, you have to compare the cost of energy from the utilities that you currently buy from against the first costs of putting in the system, so the capital investment. And then you have to look at potential energy cost savings that you may get through your on-site generation options. So this would be not just electricity generation, but also recovery of heat. And then we're also looking at the savings that you get by billing through a single metering point. Now, the variables that you have, obviously, if you own a lot of utility infrastructure, there are going to be some maintenance factors that you have to look at. We'll look at that a little bit later in the presentation. And then there are some intangibles. So you can put a price tag on everything up to this point in the discussion. Now we're looking at reliability. You can significantly increase your on-campus reliability if you put in your system designed the way you want it with an appropriate amount of redundancy. So maybe you can't put a price tag on it, but you certainly know what happens when you lose energy to the campus and you cannot perform your duties every day. So there's certainly an intangible cost to that. So let's talk a little bit about how electricity is priced, the cost of electricity. So what is metered and what is billed for? So the biggest thing that's billed for on an energy bill is the energy itself in kilowatt hours. Then also utilities will typically bill a larger customer for the kilowatts. We equate that to work. It really is just a measure of the amount of kilowatt hours that are being used at any one time. And then in some larger rate schedules, there's also a charge or a penalty for what's referred to as reactive kilovolt amperes, sometimes known as RKVA. We're not going to go into any great detail on that, but that typically comes into play on industrial rate schedules. So what are the components of a typical utility bill? The utilities, since the deregulation period in the 90s, are basically unbundled vertical utilities. So we've got a generation component, we've got a transmission component, and we've got a distribution component. So your bill will typically have a basic customer charge, which is a monthly fixed fee. Then there'll be distribution charges for both the kilowatts and the kilowatt hours used. There'll be generation charges for the kilowatts and kilowatt hours used. And then there'll also be a transmission demand charge for the use of the transmission system to wheel the power from the source to the user. And then, of course, in addition, there'll be some riders and taxes that vary by state and by jurisdiction. Let's talk for a minute about the power of aggregation. Like most things, electricity when purchased in bulk becomes cheaper. So when you aggregate a lot of loads together, you can take advantage of some features in most rate schedules that will help you get a better cost on your energy. Low voltage rate schedules are built with bracketed charges that benefit larger users with level demand curves. So what do we mean by a level demand curve? So during the day, a building is going to have a load curve that goes up as users come in and as temperatures change, and it'll level off at some point, and then at some point it'll peak, and then as users leave the building and stop using it, lights go out, temperatures become more mild, the load will go back down again. So during a day, we have what we call a diurnal load curve, and it will vary from building type to building type, but all buildings have it. The flatter you can make that curve, the better your cost per kilowatt hour ends up being in most utility billing schedules. So The idea is to try and level the loads, fill in the valleys, and clip the peaks off a little bit to get yourself a more steady load curve. Aggregated power demand tends to level out the load curve. So if you think about several different building classifications that have different types of loads and different types of usages during the day. So think about the types of buildings that are used most heavily during the middle of the day, then think about the types of buildings that are used most heavily after hours, and you can imagine that they're going to peak at different times. A perfect example is a football stadium. That peaks at night when the lights are on during games, has very little load during the day. So if you mix together classroom buildings, recreational buildings, administration buildings, sports facilities, and other types of facilities, then what you end up with is you end up with a flatter load curve that tends to fill the valleys and take the peaks off. When you do this, it tends to make it so that you can get a better cost per kilowatt hour through most utility rate schedules. So up on the screen right now, I have got a picture of a corner of a typical campus. And to describe what we're looking at, we have two classroom buildings, one larger, one smaller, and then we have a sports and recreation facility. The site is bordered by a utility-owned distribution line, an aerial line at 12.47 kV. And then on the site, we have the services to each individual building. So each individual building has its own transformer, has its own service, which is shown in the yellow dotted line. And then the blue dotted lines shown on the ground are the primary or distribution voltage lines coming from the utility. So they start at one end of the pole line, they go through the three transformers, and then they come back to the other end, creating a loop. Each one of these buildings in this scenario has an individual meter, and the owner of the utility or the owner of the campus receives an individual bill for each of these buildings every month. So let's take a look at what the load curves look like on these buildings. So right now in a chart we have in front of us, we've got the load curves for our three buildings. So in the yellow and red, we've got our two classroom buildings, one a little bit bigger than the other. You see that those load curves are relatively consistent. The buildings are doing the same thing at the same times of day, therefore they're tracking fairly closely with each other. One building's just a little bit larger than the other. The curve in blue is for our sports recreation facility, and you see that its load curve goes up as the temperatures change during the day, but it doesn't really peak until after hours when people are really using the facility for recreation. So what you see here is an opportunity. You've got some peaks that are non-coincident, and therefore you can put them together to lower your overall peak. So if you look at the curve in green, that's your composite demand where we just simply added the three loads together over a period of 24 hours. And you'll see you've got a peak somewhere around 3:30 in the afternoon. Now, if you look at the blue line on the very top of the graph, this is just a straight addition of the peaks of each of our three buildings. Now, if you look at the difference between the cyan line at the top of the screen and the green line that represents the composite peak, you'll see that there's actually a demand reduction in 70 kW. This is purely because the peaks are non-coincident and you're able to take advantage of that. This is a bit of an excerpt from a rate schedule. We've used one from Dominion Virginia Power, but most are fairly similar. We have a column on here for each of our buildings, and we also have a column for a composite. So what we did was we just added together the loads during the day that were represented by that green line and pretended we had a single meter. We're using the same rate schedule for all these comparisons. And so what you'll see is if you look at the three buildings and you go down to the average cost per kilowatt row, you'll see that you're paying about 11.1 cents down to about 10.6 cents per kilowatt hour for each of these buildings. When we aggregate them together and just put them through a single meter using the very same rate schedule, you'll notice that all of a sudden we're paying 10.26 cents per kilowatt hour, and we've got a savings of 7% on our energy. So for over a month, we'd save almost $1,400 on these three buildings simply by putting them under a single meter. So that's not insignificant. Now the savings really add up though when you go to a higher voltage level. So let's take a look at this same three building clip, and we've got the same overhead distribution line going around the campus, but this time what we've done is we have assumed ownership of the on-site distribution system. So you know we've got the same three transformers, the same service facilities shown in the yellow dotted lines, but now we've got a primary metering cabinet up in the upper left-hand corner of the system, and the red and blue lines represent a campus-owned distribution voltage utility system. So everything is virtually the same. The only difference is that we now own the on-site infrastructure. Let's see what that does to our rates. So now what we can do is we can go through rate schedule GS4, which is a large general service primary voltage rate schedule. This is the very same load curve, the aggregate load curve that was shown in green earlier. And you'll notice now that we're showing a 27% savings in energy, and we're showing a cost per kilowatt hour right at 8 cents. So if you'll remember, we were looking at somewhere between 10.5 and 11 cents per kilowatt hour. All of a sudden, we're down to 8 cents per kilowatt hour. And this is simply by owning the infrastructure and aggregating through a single bill. This is the power of aggregation over a 3-building section. Think about if you have 30 buildings. Think about if you have 50 buildings. So this is a pretty powerful concept. Now, incorporating generation once you own your on-site campus utilities can add even more savings and make your energy mix even more cost-effective for your institution. So in this picture, what we've got is a diagram of a typical turbine generator connected to a single building or a single switchgear. And what we're doing here is we're doing what we call a peak shaving scheme. If you remember earlier, we talked about the concept of being able to level the peaks and fill the valleys. So at certain times of day, you can run the generator to do absolutely that. So we can start to flatten off the peaks and avoid some of the penalties that are in the rate schedules to get ourselves a better rate on electricity. So basically what we do here is it backfeeds into the electric system through a building's service facilities. So if you watch the power flow on the diagram, we've still got power flowing through the transformer into the building, and then we've also got power flowing from the generator into the building. So it helps us to do a net metering effect and offset the peaks. So here's a picture of what that building's load curve looks like. So if you follow the load curve on top, that's without generation. That's the diurnal load curve throughout a 24-hour day. If you turn on a block of generation, which is shown in the green block at the bottom of the diagram, you notice that you offset the peak during the center of the day. Now, what you do ideally is you make this correspond to the penalty periods in your rate schedule. So basically, you're taking advantage of loopholes that are built into the rate schedule by generating during times when energy costs you more than it normally would. So this is a peak shaving scenario, the simplest way to use generation. This next scheme is a combined heat and power scheme. This is more of a prime power type of arrangement where you're actually providing significant energy to the campus through your generation system, and you're typically running this 24/7. So in this particular diagram, what we've got is the same turbine generator setup, but now we're putting our power into a primary voltage switchgear that feeds multiple feeders on campus. And then the key here to making this work is we are capturing the waste heat from the generator. So generation systems, be they turbine generators or diesel generators, have a great deal of lost heat that goes out the exhaust. This system captures that heat to increase the overall energy efficiency of the system, and that heat can be used to generate steam at your central plant. It can be used for hot water for domestic use. It can be used in absorption chilling for your chiller plant. Or we can do something called an organic Rankine cycle turbine, which is a closed-loop system that actually uses a refrigerant cycle to drive a generator based on heat input from a waste heat stream like an exhaust of a turbine. So using cogeneration as prime power depends on a couple of things. You've got to have thermal efficiency, and you also have to have a year-round heat client. And what we're talking about with the heat client, if you get a large enough campus, you're running your steam system every day of the year for something. It's either being used for domestic water, it's being used for reheat coils in buildings, but you've got a significant steam load all the time. Also, if you use absorption chilling, then you still have a reliable heat load that runs all year long. If we look at our energy conversion efficiencies, this really shows the picture for payback using generation. A simple gas turbine generator with no heat recovery, where we just simply eject the waste heat up the stack, is somewhere between 28 and 38% efficient. What this means is that the gas you put in the front end, the energy contained in that gas, we only get about 28 to 38% of that energy back in the electricity that's generated. Pretty low efficiency system. Pretty good for peak shaving though. If we augment that gas turbine with an ORC turbine, then we can get our efficiencies up to 42 or 52%. So it's getting better. But these scenarios are still both unlikely paybacks for a prime power system. If we add a heat recovery steam generator and actually put our heat into our campus steam system, our efficiencies now go way up to 75 to 85%. This is typically the system you're going to see when a campus is using an on-site generator as their prime power source. If we use a gas turbine with vapor absorption chilling, you can get somewhere in the 52 to 62% range. Still pretty good efficiencies. It may or may not pay back depending on energy costs. So let's talk a little bit about first costs of owning this infrastructure. In the utility-owned option, the campus owns none of the infrastructure. It's installed, it's operated, it's maintained, and it's repaired by the utility. There is a possible contribution in aid of construction up front depending on the service policies of the utility you're dealing with. That ranges from free to relatively expensive, but once again, it's all the utilities equipment they own that they operate. In the campus-owned option, the institution owns and operates and installs the utility system 100%. It can be a significant investment. So if we're looking at a life cycle cost analysis of energy costs versus first costs versus O&M costs versus intangibles, this is a large piece of the equation. Generation options also may be 100% owned and installed by the campus, but there are also third-party financing arrangements like shared savings programs or power purchase agreements that may offset the initial cost and return the generation as a monthly fee. So for a simple on-site distribution system, you may be looking at an investment of $55,000 to $75,000 per building to get in business. For a larger, more complex system, you may be looking at having to build a distribution substation. You might be looking at installing large amounts of cabling, switchgear, and distribution transformers. You may be moving into the range of $85,000 to $115,000 per building. On combined heat and power generation, it's going to range somewhere between $1,250 and $3,300 per kilowatt installed of capacity. Let's talk a little bit about maintenance implications. These are your variable costs. So when you own and operate your own medium voltage or primary voltage on-site distribution system, you're talking about having a higher skill level of the people that maintain and operate that system. Many campuses contract these services to qualified electrical contractors and actually have service contracts in place. Some very large campuses train and maintain their own staff to do this work, but it involves higher skilled training, more qualifications, and a much higher level of personal protective gear. These systems do require some level of engineering support. Larger campuses sometimes have these folks on staff. Most campuses hire out these services to consulting engineering companies. The other thing you have to look at in maintaining a system like this is the parts and pieces for it are not readily available at the electrical supply. So you do have to have stocking of some long lead time equipment. And you also have to keep some transformers and switch gears just in case, because they are kind of hard to come by in an emergency. In the cogeneration systems, these typically require a maintenance service agreement with the generation services supplier. Most of the OEM manufacturers also have a service division and will do a monthly service contract for you. It may also involve the addition of some permanent staff to run the system, so there are some costs associated with personnel in maintaining an on-site generation system. Reliability is our intangible. If you have very good service now and you put in your own distribution system on campus, you may not see a significant increase in reliability. If you have very poor reliability right now and you put in your own system with a good deal of redundancy in it, and you've got a lot of backups built into your system, you may get a great deal of intangible benefit from that, from lack of lost time and the ability to continue business without having utility interruptions be a problem for you. If you do the utility-owned system, you're typically going to get the utility standard design, unless you pay for extras through added facilities charges. Utilities vary greatly in the reliability of their standard design. Some are very single-ended and really have lots of single points of failure. Some will provide some redundancy at no charge. So it really depends greatly on what utility that you're dealing with. If you put in your own system, you get what you pay for. You can build in as much redundancy as you can afford and as much as you want, and it can be custom tailored to your needs. You may or may not be able, however, to mitigate upstream issues. So if you're connected to a poor reliability distribution line that also serves, say, 7 subdivisions in a shopping center, runs down a busy street and gets hit by a car once or twice a year, there's not much you can do on site to make that go away. So you may be able to negotiate with your utility to get an express feeder or a more reliable source brought to your site. So that's the end of our presentation material. I'd like to do a quick recap with you about the topics that we've covered today. First topic that I would like to emphasize is the power of aggregation works. So when you're looking at aggregating your loads under a single meter, it's going to make a significant difference. If you recall, our example actually showed a 27% savings in the cost of electricity. A higher load factor reduces your cost of electricity. So anything you can do to manage your peaks and valleys will get you a more advantageous energy price. Purchasing electricity at the distribution voltage typically results in significant savings. So you should consider, if you're doing an expansion or a major renovation on campus, looking at the possibility of putting in your own distribution voltage system. Considering a total energy picture might be the solution. You should always examine possibilities for on-site generation if you're looking at a significant energy infrastructure investment. Heat recovery makes your on-site generation life cycle cost analysis much more attractive. So anything you can do to recover the waste heat made through generation processes is going to make your energy picture look much, much better. And always remember that there's a lot of moving parts in this decision, so a complete life cycle cost analysis is always required before you decide on a path. So that concludes our presentation. I'd like to thank everybody for attending today. I hope this has been informative and thought-provoking. We welcome your questions, and you can also contact me via phone or email, and I'll be happy to answer any of your questions. So time of day rates are a way that utilities have to incentivize their customers to use the most electricity in periods when the utilities are most prepared to do so. So you may have a peak time of day, say for instance in the summertime, early to mid-afternoon tends to be a peak time for a utility. So they may design a rate schedule that incentivizes you not to use a lot of power during that time of day by making it extremely expensive. So if you have the ability to, say for instance, peak shave using a generation system, let's say that they say peak times are between 1 o'clock in the afternoon and 6:30 in the evening. So if you can run a generator during that time period, shave your peak down to a reasonable level, you may be able to save yourself significant costs by participating in a time of use rate schedule. So typically, if you have an institutional campus, you're going to have a representative at the power company that is usually your commercial power representative. So in that case, you start the conversation by calling that person saying, hey, we're thinking about incorporating generation into our facility, and we'd like to talk to you about rate schedule options that might be advantageous to us if we reduce your peak for you. So typically those folks will do a rate schedule comparison for you, and we'll go through the different scenarios. If you say, hey, I want to put in 500 kW of generation. How good would that be if I went on your time of use schedule and agreed to run the generation during that time period? You may also be able to participate in some curtailment programs offered through utilities. They may actually pay you just to have reserve generation on site so that when they're having a system emergency, you agree to remove a certain block of load from their system in exchange for a monthly payment that is given to you whether you use it or not. So there are a couple of options that usually a utility representative can make clear for you and help you evaluate your options to see if it does pay off in a life cycle cost analysis. There are standard measures for reliability. There are some that are recognized by the industry that are usually measured at the utility's service entrance, and these typically have to do with availability, dealing with things like outage minutes and frequency of outages. And then also once you get into your on-site infrastructure, there are also the IEEE, the Institute of Electrical and Electronics Engineers, also publishes standards that actually get down to availability, which basically puts it out to the number of nines percentage of time that your utility infrastructure is available for you to use, and there are equations and methods for calculating that based upon the amount of redundancy that's in your system. So chilled water storage is an interesting concept. It works very, very well with time of use schedules, and it also works very well with on-site generation. So imagine that you can make your chilled water to circulate on your campus in hours when electricity is very, very cheap. So let's say that the utility offers you an amazing bargain for using electricity overnight. So you can run your chillers overnight, and then you can either store chilled water or you can also store ice overnight. And then during the day, you don't actually run your chillers. All you do is melt the ice or circulate the chilled water through your system so that you can take advantage of having a very low demand during the time of day when the electricity costs the most. So this is often used at large facilities and large institutions, and it tends to be a pretty good strategy.